You may have noticed in the previous video that every example I showed assumed that interest was paid just once a year. We would get 6% interest per year on $1,000 deposited, so we'd get $60 interest in that first year. But annual interest doesn't always have to be the case. Interest could be paid or compounded more frequently than just once a year. In this video, we're going to discuss how to handle those situations where you pay or receive interest more than just once a year. We first need to define some terms. First, we have the annual percentage rate, or the APR. The APR is the interest rate quoted in yearly terms, the interest rate per year. It's sometimes called the stated rate since it's the rate that often appears on things like credit card statements, loan documents, and bank accounts. The periodic rate is an adjusted rate that takes into account that interest may be paid more than once a year. To get the periodic rate, we simply take the APR and divide by the number of compounding periods within a year. If we pay interest twice a year, the compounding periods per year would be 2. If we pay interest monthly, it would be 12. It's important to note that the periodic rate is the interest rate you should use for I in all time value of money calculations. Whenever you see an I in the formula, you should immediately ask yourself, what is the periodic rate? And the frequency of the compounding must match with the frequency of the periodic rate. So if we get interest once a day, then we have to have a daily rate. If we get interest monthly, we have to have a monthly rate. So how do we find periodic rates? It's actually really simple. All we're doing is we're dividing the annual rate, the APR, into pieces. Daily pieces, monthly pieces, quarterly pieces, whatever the frequency. Doing that will give us a rate per period, a periodic rate. Let's do a few examples to show this. Say we have an APR of 12% and interest is compounded monthly, so we need a monthly rate. We would take the APR, 12%, and divide it by 12. That gives us a periodic rate of 1% per month. What if we get interest once a quarter? So we'd need a quarterly rate. We would divide that 12% annual rate into 4 pieces and get a periodic rate of 3% per quarter. And if we get interest every day, we would need a daily rate. So we would divide the 12% APR by 365 days and get a periodic rate of 0.0329% per day. You might be looking at all this and wonder, what's the point? If all we're doing is breaking up an annual rate into pieces, what difference does it make? Well, compounding frequency has an impact on the value of the investment you're evaluating. Let's do some examples to illustrate this. Say you invest $1,000 into an account that advertised an 8% APR. How much is going to be in the account after 5 years if interest is compounded semi-annually? Since interest is compounded semi-annually, that means we need a semi-annual rate. We take the 8% APR and divide it by 2 semi-annual periods per year. And that gives us a periodic rate of 4% per semi-annual period. Now we can compute the future value of this investment. We're going to start off with $1,000, so that's going to be the present value. The I is going to be the 4% semi-annual rate we just solved for. And N will be 10 semi-annual periods. It's important to notice that the time units on I and N match up. We're not investing for 10 years. Instead, we're not investing for 5 years. Instead, we're investing for 10 semi-annual periods. I think it's always good practice to always specify the time units next to the number as I did here. 4% per semi-annual period and 10 semi-annual periods. This helps to make sure that you remain consistent with the units. Finally, we're solving for future value. Putting the values into the future value equation, we get 1,480. That's what's going to be in the account at the end of the 5 years. Let's do the same problem, but change the compounding frequency from semi-annual to monthly. So we need a monthly rate, so I'm going to divide the 8% APR by 12 months in a year, so we get 0.67% per month as our periodic rate. 0.67% per month is going to be our I, and our N will be 60 months. Remember, we have to be consistent with the time units. We'll be investing over 60 months, not 5 years. Computing future value, we get 1,489, a little bigger than 1,480 that we got for semi-annual. We'll do another one. What if the account paid interest daily? So we need a daily rate. That's 0.02% per day. And we need N in terms of days. So how many days are there in 5 years? 1,825 days. Solving for future value, we get 1,491. Again, a little bit bigger. We can make the compounding frequency faster and faster. Instead of getting interest every day, we could get it every minute, or every second, or every nanosecond. However quick you want the time periods to be, you can do it. Continuous compounding is the limit. It's as fast as you can possibly go. Continuous compounding represents getting an interest payment at every single possible instance of time. And we can find out the future value of an account that pays simple interest by using the exponential function e. We could say that the future value of an investment with continuous compounding can be found as the present value times e raised to the APR times the number of years invested. Continuing the trend of the previous examples, we'll see what happens if that same account pays interest continuously. We have the present value of $1,000 times e raised to the APR of 8% times 5 years. And that gives us 1,491. A little bit larger than what we had with daily compounding. We can summarize all the results here. We can see as the compounding frequency increases, the future value increases as well. But why is this the case? Why does the future value increase as the compounding frequency increases? Well, it all has to do with having more opportunities to earn interest on interest. Let's try to illustrate it here. First, we'll do a standard problem. We deposit $1,000 today, and I want to find out what it's going to grow to after 1 year. With annual compounding, that means we get interest just once a year. So if the APR is 8%, the periodic rate is also 8% per year. We find that the future value of this is $1,080. Now let's do the same problem, but with semi-annual compounding. Semi-annual compounding means that we'll break the year up into 2 half-year pieces. And we're going to earn interest in each of them. That's 4% per semi-annual period. Now let's find out what we're going to have in the account after each of these semi-annual periods. After the first 6 months, we're going to get 4% interest on the investment, which gives us an interest payment of $40. So our account balance after 6 months is $1,040. And remember, with compound interest, we earn interest on accumulated interest. So over the next 6 months, we're going to get $40 in interest, plus 4% on the $40 we earned in the prior period, giving us a total of $1,081, about $1 more than if we just had annual compounding. If we broke this year up into quarters or months, we would have even more opportunities to earn interest on interest, and thus we would have a larger future value. Try it out yourself to check that it works out. Try this with monthly compounding or daily compounding, and you'll see the future value is going to get bigger and bigger. You might end up in a situation where you need to compare interest rates that have different compounding frequencies. One bank pays daily interest, whereas another bank pays monthly interest, for example. We wouldn't be able to compare APRs since APR doesn't take into account the compounding frequency, and as a result may understate the rate that's actually earned. So instead, we can compute something else called the EAR, the effective annual rate. This rate will reflect the rate you would actually earn from each bank, taking into account the compounding frequencies. These EARs would be comparable across the banks. To compute EAR, we would apply this formula here. The effective annual rate is 1 plus the APR divided by M raised to the M power minus 1, where M here represents the number of compounding periods in a year. We can also find the EAR for continuous compounding by doing E raised to the APR minus 1. Let's do an example. Say we have an account with an APR of 12% that's compounded monthly. The effective annual rate on this account will be 12.68%. Notice that the EAR is greater than the APR. This is because we're actually earning more than the 12% that's stated due to the compounding, earning interest on interest throughout the year. If the account compounded interest continuously, it would have an EAR of 12.75%. Again, notice that the EAR here is even greater than what we had with the monthly compounding. Again, this is because there's more frequent compounding in this continuous case. More interest on interest throughout the year. This table here summarizes the effects of compounding frequency on the EAR. And as you can see, as the compounding frequency increases, the EAR increases as well. We'll wrap up with an example in which computing the EAR can come in handy. Let's say you're shopping around for a bank account and two of them catch your eye. One bank pays 5.25% APR with daily compounding, and the other pays 5.3% with semi-annual compounding. Which one of these is going to pay the most interest? Notice that we can't directly compare the APRs. The second account has a higher APR, but less frequent compounding. So better in one dimension, but worse on the other. The only way to make these rates comparable is by converting them both to effective annual rates. So the EAR on the first account is 5.39%, and the EAR on the second one is 5.37%. Now these rates are comparable, and we can see that the first bank is the one for us. If we put our money in there, we'd earn more interest. It's very important that you pay attention to compounded frequencies. As you've seen, these details can dramatically impact the results you get and can impact the decisions you make.